In this module, I'm going to continue from our introduction to algorithms earlier, and we're going to focus on the notion of complexity of algorithm. I'm going to briefly define the big O, big omega, and big theta notations, and uh, look at how we can compute complexities of some algorithms. Our goal in this class is not necessarily to evaluate complexity of a given algorithm, but just to understand how the complexities work and look at how different complexities compare with each other. You will study the complexity notion in 331 further, where you will study complexities of different algorithms. So, what is the complexity of an algorithm? The complexity of an algorithm is the cost of the algorithm measured in some parameter. Now, generally, we have two parameters that we care about: how long it takes and how much storage, how much memory you need. Now, when we compute complexity of a particular algorithm, generally what we care about is the number of operations of specific types. So, for example, in matrix multiplication, I might care about the number of multiplications because multiplication is much more expensive than addition, things like that. As a rule, when we compute the complexity, what we are trying to capture is either time or space, but we often create a shorthand for it by just looking at certain kinds of operations because those are the operations that we know is going to affect the overall running time or the space required. To express the complexity, we need to understand what are the cost parameters. We need to decide on that. We also need to design how we are going to express these cost functions, and we will look at some examples of this on the next slide. To compute how much complexity of an algorithm is, it's going to depend on how we represent our data. So let me give you an example. Let's say we have the task of adding two numbers, and our another task is decide whether a number is even. So let's look at how we represent numbers. One way we can represent number 12, we can write it using our usual or decimal representation, which is digit 1 followed by digit 2, or we could write a long representation, which is 111 repeated 12 times. Now, the time it will take to do addition or to decide whether a number is even is going to be affected by how we represent the numbers. So, for example, if it's represented using something like 12, then I could check whether a number is even just by looking at the last digit. This will require me to count stuff, etc. In general, unless otherwise stated, and in fact for this class all the time, we will assume that the representation is like the usual representation, either in terms of decimal or in terms of binary, etc. It turns out that the complexity class will not be affected by whether I use decimal or binary numbers, and so we'll always stick with this. We will not use this unary representation because it can affect how we measure the complexity, and unary representation is not an appropriate representation for almost everything that we do. Now, what we are interested in complexity of an algorithm, especially because we are not computing it precisely, we want to get an idea of how an algorithm behaves, is we want to know how good an algorithm is when the input happens to be very large. So, what complexity of an algorithm is trying to capture is how does the algorithm behave, not when the inputs are very small, since when the input is 3 4 5, but when the input number is very large. So if I'm thinking about A graph algorithm, I want to know how the algorithm behaves when the graph has thousands or millions of nodes. I don't particularly care for special algorithms where the graph has only 3 nodes, because in that case, the analysis that we are going to make is not perfect enough, and maybe we need to make more precise analysis of the algorithms. First thing we are going to do in here is we are going to introduce the big O notation. The reason we call it a big O notations is because there is also a little o notation. We won't get into that in this class, but it's something that you might come across in other places. We are going to look at big omega and big theta notations. Before we get into big omega and big theta and big O notation, I want you to review this slide, print this slide, and understand what's going on. What this slide is talking about is logarithms and its properties. It's something that you have seen before, but it is something that we would use quite a bit in this module as well as some of the modules in the future. So it would be a good idea to be aware of what's going on in this slide and remember these things. Okay, so big O notation, what it allows us to do is it allows us to suppress unimportant details and concentrate on the most important features of the algorithm, and we can do that without really losing the big picture. So we have quite a big definition for big O. So it is a function fx is big O of another function gx. We write this as fx is big O of gx. We read this as f of x is big O of gx if we have the following property. The property that I want is fx is less than or equal to c times gx for some c. But I don't want this for all values of x. I want it only for large values of x. And what do I mean by large? I mean I want it to be true for all x greater than certain value k. So let's step back and look at this definition again. So what we have is we want to be able to find a c and a k. We want to be able to find a c and a k such that when x is greater than k, fx is less than or equal to c times gx. If we are able to do that, we will say that fx is big O of gx. So what is big O notation? What is it trying to capture? When we say fx is big O of gx, we mean that f does not grow faster than g after a while. So that is when the numbers are large, f grows at the same rate as g or maybe slightly slower than g. Let's look at an example. We want to show that f of x is big O of x cube, where f of x is x cubed divided by 3 plus x squared divided by 2 plus x divided by 6. So what we can observe is if I assume x is greater than or equal to 1, then x cube is greater than x square is greater than x. That means I can see that f of x is less than this term where I have replaced x square and x cube where I have replaced x square and x by x cube. Now if I add this up, these terms add up to x cube, and that means I can set c is equal to 1 and k is equal to 1, and I can show that fx is less than or equal to 1 times x cubed whenever x is greater than or equal to 1. And that means f of x is big O of x cubed. Note that I could have been sloppy and write it as fx is equal to big O of x to the power 10. Nothing in the definition of big O requires us to give us the best possible bound. So in this case, I could have written that this is big O of x to the power 100 or x to the power 1000, 10,000, etc. Our next example is to show that log n is big O of mth root of n, where m is any positive integer. So we'll do it using the properties of log that we identified earlier. Now this proof works as follows. First, I'm going to observe that n is less than or equal to 2 to the power n minus 1 for any positive integer n. I can take log of to the base 2 on both sides. That will give me log n is less than or equal to n. Now what we are going to do is we are going to play with this thing and do some standard arithmetic thing and use the properties of log. So log n is, I can multiply by m, divide by m, so it's equal to still log n. Now the way I'm going to do this is I'm going to take one of the m's and take this inside. So this m I'm going to take inside. That will give me m times log n to the power 1 divided by m, which is m log mth root of n. Now I can replace this term by this term because that's exactly what we showed earlier. Log of n is less than n, so log of mth root of n is less than mth root of n. So we can replace it like that, and that means log of n I can show is big O of mth root of n. Review this proof. If there are questions, please put them on Piazza, as well as we'll discuss this in class as well. This proof is somewhat non-trivial in some sense, especially if you're not familiar with properties of log a lot. So if there are questions, please do ask in class or on Piazza. Once again, we have reached the check before you go ahead slide. I want you to understand what the big O definition is, and I want you to see how we found the values of c and k for the different functions that we looked at earlier on the slide. Note that the values of c and k are not unique. You would be able to find different values of c and k, and this is one of the things I would ask you to do to see if there are other values of c and k that you can identify.